Today we'll talk about graph games. Let's see. What is graph game? Graph game is basically a game on a graph. So we have some graph and you want to play some game with it. There are different graph games. Today we'll discuss some classical graph games. The most classical graph game looks like this. You have some graph. You have a directed graph. Something like that. And you play the following game. You have a special token. It is placed in some vertex of the graph. Like this. And there are two players. They take the alternate turns, and when it's your turn, you just move the token along some edge. So for example, now the first player moves the token here. Then the second player turns, and the second player moves the token here, and so on. When you have nowhere to move, when there is no edges from your current vertex, you lose. No move, and then lose. Something like that. Very simple game. And the question is, if you put the token here, who will win if both players play optimally? So there are two players, and there are no ties. So in every game there is some final node, so there is nowhere to move. So if there is no tie, then one of the players will win. So the question is to determine who will win if you place the starting token here. Cool. So let's try to analyze these games. First, games to analyze are the games. Then you have a cyclic graph. So if you have a cyclic graph, in a cyclic graph, most of the games are very easy to analyze actually. For example, in this game, how to analyze this game? If you have a cyclic graph, why is the game infinite? Yes, if you have a cyclic graph. If you have cycles, you may have infinite game. Yes, right. If the graph is cyclic, there is always the winner. You cannot have a tie because the game will finish at some point. Yeah. So first, if you have a cyclic graph, then most of the games are very easy to analyze. That's because you have, of course, if you have a cyclic graph, you can make a topological sorting of this graph and just go from left to right or from right to left and analyze games in this order. So let's put some numbers here. So there's 1, 2, 3, and 4. So you make a topological sorting of this algorithm or of this graph, and then we'll go from right to left and analyze the games starting in this node. So if we start in node 4, then we will immediately lose, right? So if you start in node 4, there's a losing game. So if you start here, you lost the game immediately, yeah? So this is a losing node. Let's mark it as 0. So 0 means that this node is a losing. If you start the game in this node, you will lose the game. So the first player will lose the game, right? Now let's move back. Let's move to node 3. For node 3, you can move to node 4. And if you move to node 4, then your opponent will lose the game because node 4 is losing game. So if you start in node 3, your game will be a winning game because you start from here, you move to the losing node, and your opponent will lose. So, so in node 3, you have a winning game. Did we choose where to start? No. There is some fixed starting vertex. So one of the nodes, let's say is node S. This is starting node again. But we will analyze all the nodes. So for each node, we will determine if the first player will win if we start in this node. and we just analyze it from right to left. So for each node, we will determine if you start in this node, will you lose or will you win? Yeah, that's the plan. Let's move next. So now if you have node 2, so if you start the game in a node 2, then you have two options. The first player has two options. He can move to node 3. If he moves to node 3, then he will lose the game, right? Because I move here and then my opponent will win. Or I can move to node 4, and if I move to node 4, I will win the game because my opponent will lose the game. So out of these two options, if you are the first player, you will decide to go to the losing position and to win the game. So node 3 is the winning game because you can move to this position and your opponent will lose the game. So node 2 is winning game. Now in node 1 you have two options, but in both these options your opponent will win the game. So you can move here and lose, or you can move here and lose. So in both these cases you will lose the game. So vertex 1 is the losing game. That's all. That's how you analyze this game if you have a cyclic graph. So again, what you do, you go from right to left. You take some node V. You look on all edge. So you just iterate over all edges going out of this node V. If at least one of these edges go to some losing node, then you can make this move and win the game. So your game is a winning game. And if, let's say, if all your moves go to some winning game, then no matter what move you make, you will lose the game, because in each case you will go to some winning position, so your opponent will win the game. So this is a losing position. That's all, and now you just apply this from right to left, and you will decide for each node if it is a winning node or it is a losing node. That's the whole plan. That's the whole plan. Clear enough? Now, for a cyclic graph, many other games are also easy to analyze. For example, if you have, let's say, you have something like this. Let's say for each node, for each edge, there is some cost. Let's put some integers here, so you can, let's do 7 here, and for example, 4 here, or you can move here, let's say 1, and one place, let's say 3, and then 5 here, doesn't matter. Let's say each edge has some cost. So when you make the move, you pay this cost to your opponent. Yeah. So for example, I start here. I make this move. I pay $1 to my opponent. Then he makes this move and he pays me back $3. And then I make middle and I pay him back $4. So if I make this move, then he makes this move, and then I make this move, my total winning will be 1 minus 1 plus 3 minus 4, so it's minus 2. So if I make this move, then he makes this move, then make this move, I will lose $2. Yeah. And the question is to find out what is the maximal possible profit I can get in this game. So if both players play optimally, you need to estimate the maximal possible winnings of the first player. Let's go. So how to analyze such kind of problems? The same way we analyze these problems. So we just make a topological ordering. Now go from right to left. For each node, we will find the value, let's say D, will be the maximal winning of first player. That's all. That's how you do it. Now, again, how to find this value? You have this node V. You look on all outgoing edges. Have this. Let's say we have node U here. So if you make this move, then you will pay the cost of this edge. So your winnings will be minus weight of the edge. And then your opponent starts from here. So he will pay you back. So he will win the value of this node. So the du will be the optimal winnings of the second player. Your winnings are his winnings are your losings. So your winnings will be minus du. And now you just take maximum of all these values. Can you make this problem a bit harder by adding limit, like you win if this happens when you counting moves is odd? No, there are many modifications of this problem, and most of them are easily solvable by the same approach. So just you make topological order and go from right to left. So basically, if the result of the game only is determined by your current position and not by the history of all moves, then all of this game are easily determined by the same approach. Some more complicated game may so sometimes your move depends on all the previous moves. So your current move depends on the history of moves. Then it's a little bit more complicated. So you somehow need to remember the history of all moves. Sometimes it's possible, sometimes it's not. But in these problems, my choice of move only depends on my current position. So no matter what happened before I enter this position, my move is easily determined only by this position. So I just need to make this dynamic programming based on the current node of my game. Makes sense. Let's apply this to this graph. So I go from right to left. So here there is nowhere to go. So the game just stops and my winnings is 0. And now for vertex 3, I can go here. So I will pay $4 and my winnings will be -4. Here I have two options. I can go here, pay $3 and then get $4 back. So my winnings will be 1. And if I go here, then I pay $5 and get nothing. So my winnings will be -5. So I take my maximum of 1 and -5, maximum is 1, so 1. And now for node 1, I can go here, pay 7 and then get -4. So my total winnings will be 7 plus 4. That's too much. Let's do it like this, just to make it more interesting. So I can go here, pay 1 and then get 4 back. So my total winnings will be So my total winnings will be 3. Yeah. So 3. So I spend 1 and then get 4 back. Or I can go here. Yeah. So I will pay 7 and then and then get another and then lose 1. Yeah. So my opponent will win 1, so I will lose 1. So I will pay 7 and then lose 1. So okay, it's not very interesting. Okay, so I pay 7 and then spend 1. So I will lose 8, right? So I will lose 8, and here I will lose. It was better, right? Let's move back. Sorry, I'm not very good at this. Examples. I just want this example to be interesting, but so here I pay 7, then get 4 back, so my winnings is -3. here I spend 1 and then get 1 and then spend another 1. So my winnings is -2. So here my winnings is -3. Here my winnings is -2. Yeah. -2 is better than -3. Yeah. So the result will be -2. Good. So the optimal strategy is go to. So the optimal strategy for the first player is to go here. The optimal strategy for the second player is to go here, and the optimal strategy for the first player is to go here. So total winnings will be -2. Good. That's all. Now, there are a few standard modifications for the graph games. First modification is a symmetrical game. So this game is a symmetrical game. So both players have the same strategy. Yeah, because both players can make the same moves. But in some problems, players can make different moves. So one player make one type of moves, another player make another type of moves. Oh, let's have something here. Let's use two colors. Let's use blue and red color for different types of moves. No, let's make something like this. So let's have blue here, and then move, for example, only here. And here make something like this, and also like this. And whatnot. Will it be interesting now? Good enough. Good enough. So now we have two types of moves. First player, let's say first player is red player. We have two players, red and blue. Let's say first player is red, and the second player is blue. And now, how to analyze such type of games? So if you have a symmetrical game, you want to find something like this. So you want to find for each game if it is winning or a losing game. But here you have, since the game is asymmetrical, you want to find this for both players. So each game can be winning and or losing for each of these players. So I will find two values. For each node, I will find two values. If it is game winning or losing for the first game, for the first player, and if it is winning or losing for the second player. Ничего не понятно. Грустно. Приходите во вторник. Там все по-русски. Okay. Now, I will put two values for each node. For each node, I will find two values. If it is winning or losing for the first player, and if it is winning or losing for the second player. So again, I just move from right to left and find these values. So for node 4, if I stand here, then the game is losing for both players. So it is losing for the first player and it is losing for the second player. Now, for node 3, if I'm standing here, then for both players can go to node 4. Yeah? So for both players, node 3 is a winning node. So it is winning for node for second and for the first player. What's problem statement? Yeah, problem statement is simple. I have the same game like the first game. So both players make moves, and if you have nowhere to move, then you lose. Very simple game. If you stand in a vertex and there are no outgoing edges, then you lose. But here you have two types of edges. You have like blue edges and red edges. Blue player can only move along the blue edges, and red player can only move along red edges. Now, if I stand in node 2, then if I am the first player, if I'm the red player, I can move here and win, and lose. Or I can move here and win. So the first player has two options. So he will decide to move here and win the game. So for the first player, this game is a winning game. And for the second player, this is a losing game, since the second player can only move here, so he moves here, and now the first player will win the game. So if you're the second player and you're standing here, so you move here, and then the first player will win the game. So your game is losing if you're the second player. That's all. And now if you stand here, if you're the first player, you can move here or here. If you move here, then the second player will lose. So for the first player, this game is a winning game. And for the second player, you can only move here. And if you move here, then the first player will win the game. So for the second player, it's also a losing game. Nice? Oh yes, it's a nice word. Just got it from the last Christmas gift from JetBrains. That's all. That's how you analyze the game if you have a symmetrical game. So if the game is symmetrical, you just apply this. Another way to analyze asymmetrical games is the following games. So let's just reduce our game to the simple game. So we have asymmetrical game. Let's build the same symmetrical game which have the same result as your game. How to build symmetrical game from asymmetrical game? You basically need to duplicate your graph. So you have the first layer of your graph and the second layer. And now you simply say that if you're standing in one of these nodes, then there's the first player who moves. So here the first player moves, and here the second player moves. And now we just build a simple symmetrical game. So if you're standing in node 1, and this is a turn of the first player turn, then he can move to nodes 2 or 3. And when you will move here, the second player will be the second player's turn. So you move to node 2, and there is a second player's turn. So if you're standing here and it's the first player move, then you move here. Or you can move to node 3 as well. And if it is second player turn, then he moves to node 2. So you can move from here to here. Like this. And so on. So if you're standing in node 2, you can move to nodes. So if you have the first player, you can move to 3 or 4. So you can move to 3 or 4 here. Or if it's the second player turn, you can move only to node 3, so you can move from here to here. From node 3, you can move to node 4, so you can move here and here. And that's all. And so now you have a simple graph. There is no colors, just the state of your game basically encodes your vertex and whose turn is it. Cool. Now you simply analyze this graph like we did before, like we did in the first problem we discussed. So just go for, again, this is a cyclic graph. Since you don't have cycles here, you will not have cycles in this graph. So you analyze this in the same way you analyze the first graph. So you go from right to left and mark all the nodes if it is winning, lose, or a losing node. So you start from here. This is a losing node. This is a losing node. This one will be a winning node. This one will be a winning node. This one will be a winning node, and this one will be a losing node, and so on. So this is winning. This is losing. So basically, do the same thing. So if you look on this two approaches. You basically do the same thing, but it's kind of different. Since here you need to kind of change your algorithm, just to modify your algorithm to solve your problems. And here you simply reduce your problem to already solved problem. It's usually a better way to solve the problems. If you can just reduce your problem to something you already know how to solve, it's usually a better way to solve the problems. Okay. Okay. Nice. Hmm? Hmm? No, I like the chat actually. Now, another way to unify a problem is to change the rules of the problem a little bit. So let's try to remove this for now. So let's go back to the first problem. So we just have this graph. Each player make a move, but let's change the winning condition. So let's change winning condition. So let's say if there is no move from the current node, then you win the game. So we have the same problem, but the winning condition is changed. So if you stand here, for example, then you will win the game immediately. So how to analyze such problems? What we need to change? Any ideas? So again, if we change the winning condition, so we have the same rules. They have a graph. Each player in his turn can move the token along some of the edges. And if there are no edges to move, then you win the game. How to change the solution of this problem? Easy. What? I already moderated. Okay. Let's get back to the problem. Okay. If long as they check the movability. Yes, right. The only thing we need to change is the state of the sync node. So if there is no outgoing edge, then you have some kind of dead end node, yeah? So if you're standing here, then you need to change the state of these nodes. So we'll start by marking all the end nodes as winning nodes. And now we just apply the same thing. For all other nodes, the rules are the same. So you look on all outgoing edges, and see if you can go to some losing position, then your position is winning. So these rules are the same. The only state of these final nodes will change. Okay, so we just go, again, we go from right to left, and we apply the same procedure. So for node 3, you can go only here. So node 3 is a losing node. But from node 2, you can move here or here, and you can decide to go here and win the game. So node 2 is a winning game. So let's notice that node 2 is winning no matter what conditions you look. So in both these games, node 2 is a winning node. So it may happen. So in node 2, you can decide. You can force the player to go to the dead end, or alternatively you can go itself to the dead end. So in both these winning conditions, node 2 is a winning game. Now for node 1, you can move here or here. So node 1 again. Node 1 is a winning game. we can go here and win the game. Now, again, these modifications need you to modify your algorithm. So to analyze this graph, you want to modify your algorithm a little bit. So it's a small modification, but still a modification. Let's try to avoid this modification. Let's try to reduce this problem to the problem we already solved. So let's try to reduce this problem to the normal problem. So this is the most classical game. So when you have nowhere to go, you lose the game. So let's try to change the graph in such a way that all these nodes will be a winning nodes. How can you change your graph in such a way? So basically what we need to do is to force all these final nodes to be a winning nodes. How can we force some node to be a winning node? Again, I want to reduce this problem to the first problem we discussed, when you lose, when you have no move. What we need to change? Yes, what you can do is to introduce some externals, some additional node here. And for each final node, so if there is nowhere to go from this node, you just made one special edge to this special node. And now in the first game, this extra node will be a losing node, and all these nodes will be winning nodes. And all the rest will be the same. So this is easy way to solve the problems when you have a situation like this, when you win, when you have no moves. Cool. Nice. Now let's move next. Now that's all about a cyclic graph. So if you have a cyclic graph, so basically most of the problems are easy to solve. So you just go from right to left and recalculate something in your nodes. It depends on your problem. Go. Now, what happens if you have cycles? Where's my, oh, here. What happens if you have cycles? Again, let's have some graph, and this graph has cycles, and if you have no move, then you lose the game. So the same problem we discussed, the first problem we discussed. But now you have cycles. What may happen when you have cycles? When you have cycles, you may have situation when you have ties. For example, if you have a game like this, then you have a draw. Yeah. Now this is a draw, because the game will never end, basically. So every player will have some move. So if you stand here, you can move here, if you stand here, and so on. So the game will never end. So in this case, we'll mark all these nodes as a draw. We need some special mark for this. So we have 0, 1. Let's say minus, just. Let's say D, because from draw. Yeah. Let's have, so in all these three states we have a draw game. Now draw looks like 0. I don't like it. Okay, minus is 5. Minus is fine. So now in all this game you have an infinite game, yeah? So if you start from any of this node, you will have an infinite game. Infinite game means a draw. Now, is it true that if you have a cycle, you always have a draw? So it turns out it's not the case. So even if you have cycles, the game may be a finite game. So even if you have cycles, you may have winning or losing states. For example, if you have something like that, then situations change. Let's see. So if you have something like that, then let's see. So this state is obviously a losing state. Now this state is a winning state, since you can go here and win. So this is not a draw. So if you're standing here, you can go here and win the game. So this is a winning state. And now this is a losing state, because you can only go here and lose the game. So this is a losing state, and this is a winning state. So even if you have cycles, you may have some winning or losing states in this cycle. They may be even more interesting situation. Let's say, for example, you're going to go. Let's add one more cycle here. So now what happens here? What happens to these three states? What do you think? Yes, we'll do this backwards because yes, we will do it in a minute. Yeah. I will just show you some examples just to show you what can go wrong if you just want to apply some standard algorithms. So there may be some different situations. Yes, we will apply exactly what you suggested. Yeah. So now in this game, so this is a losing state, this is a winning state. But what about these states? Now let's see. For this state, you have two options. You can go here and lose, or you can go here. You don't want to lose, yeah? So you decide to go here. From here you go there, and in this state you only go here, and so on. So for example, first player stands here, he makes the move. Now the second player moves, third player moves here. Now it's the second player turn. He don't want to lose either. So he decides to move here, and so on. So you will move along this cycle infinitely. So all these states are actually draw. So you have draw in all these three states. So this version, if you have a winning state, losing state, or draw, it depends on the structure of your graph. So these cycles may have some strange connections between them and so on. So you need to wait to determine for some nodes if they're winning or losing, and for some nodes if they are the draw state. Okay, how to analyze such games? It's actually pretty easy. What you will do? Let's try to mark all the winning and all the losing games we can. So we have some graph. I erased the cat. Sorry, it was an accident. Let's move it back. Let's make it a little bit angrier because we erased it. So now, how to analyze the games with cycles? You do the same thing like before. You try to find for each node if it is winning or losing node, and you want to do it as long as you can. So you start again. You start from the nodes without outgoing edges. If you have some node without outgoing edges, you have only outgoing edges. All these nodes are obviously losing nodes. So you mark all these nodes as losing nodes. Now you take all the nodes which has edges to these losing nodes. So here. So all these nodes must be winning nodes, since you can go here and win the game. So you mark all these nodes as winning nodes. Now, in the next layer, you want to find something special. So you want to find such nodes. So all outgoing edges go to some winning nodes. So now, if you have some node and all outgoing edges go to some winning nodes. And then this node must be a losing node. And so on. So we have some nodes like this. So these are losing nodes. And now you may have some new nodes, which has something like this. Some edges to these winning nodes. So these nodes will be winning nodes. And so on. So each time you try to add new nodes, to determine the state of some nodes. So how can you determine the state of the node? And again, like in the first game, if you have some node which has an edge to some losing node, then you must have a winning node. And if all edges goes to some winning nodes, so if all these nodes are winning nodes, then your node is losing node. Now you just want to apply these two operations, and as long as we can apply these operations. So if we can apply this operation, we apply this. If we can apply this operation, we apply this, and so on. When we cannot apply any operation, what does it mean? We applied some operations to the graph. So each time we mark some node as winning node or as a losing node. When we stop, when we cannot apply any of this operation, we stop the algorithm. What will happen in the end? In the end, some node will be not marked. If the node is not marked, what does it mean? It means that all nodes, all unmarked nodes, have some outgoing edges. Some of them are marked as winning edges, as winning nodes. And some of them are unmarked. So if there is at least one zero, we will mark it as one. If they are all ones, we will mark it as zero. So if we cannot apply this and this, it means that for each node, there are some nodes marked with ones and some unmarked nodes. And I just claim that all these nodes are draws. Because why? So because if we stand here, we have two options. We can go here and lose, or we can continue the game. And both players doesn't want to lose. So if both players, if they have the options to lose the game or to continue the game, they will decide to continue the game. So all unmarked nodes in the end will be a draws. Yes, that's exactly what you suggested in the chat. Now, let's try to do it fast enough. So I want to build an algorithm which does this thing and works in linear time. So I want to just implement this algorithm in linear time. How to implement this algorithm in linear time? I will, let's say, so we need to go from right to left again. So we go from right to left. If we have I will mark the nodes one by one. If I mark a node with 0, so if I have some node and I want to mark it with 0, what I need to do, I need to look at all ingoing edges and mark all these nodes as ones. And what happens if I mark a node with 1? So if I have some winning node here, that's a little bit more complicated. So what you need to do, so you look at all ingoing edges. Some of these nodes may become a losing node. How to find out if it is now a losing node or not? So if some of these nodes, if this is the final marked node, so we need to look at all these ingoing edges, look at all these nodes. And if some of this node now has all outgoing edges going to ones, then this node must be marked as 0. So we need to look at all ingoing edge to this node. So let's say this node V. So now we mark this node V with 1. So now this is winning node. We look at all ingoing edges, and for all these nodes, we need to find out if it was the final edge from this node. So if it is the final edge, going to some node marked with 1. So if all other edges are marked with 1, then now it's the time to mark this node as 0. So we need to find some way to quickly determine if we need to somehow find a way to determine if it was the final edge from this node. So if all other edges are marked with 1s, how can we do it? Again, first operation is simple. If you mark node with 0, you just iterate over all edges and mark this node as 1s. So it's simple. So here it's a little bit more complicated. Since you don't want to just mark all these nodes as zeros. You only want to mark a node as 0 if all outgoing edges go to some 1s. So you need to find some way to find out if after you mark this node as 1, for this node, all outgoing edges go to some 1s. How to do it quickly? Brute force will not be fast enough, since if for each node you go here and then iterate over all edges here, it will be like n squared. So you find for this node you go here, and for this node you go here. So for each node you iterate over all, for each edge you need to iterate over all these outgoing edges. So it can be, it should not be brute force, but the counters are good. Yeah. So you need to make a counter for each node. For each node you make a counter how many outgoing edges are not marked yet. And for this node you just decrement this counter and then see if counter equal to 0, then this node must be marked as 0. Cool. Let's implement this. Let's go. Now let's say we have a queue, and we will put all the operations in the queue. So in this queue we'll put all the nodes which need to be marked. First, let's put all the dead ends to the queue. So for all v, so if out of v equal to 0, then we'll say the state of v equal to 0 and put this node in the queue. Now we just put all these dead ends to the queue. And now, while queue is not empty, not queue empty, we'll take one node from the queue. If it is a losing node, then we simply iterate over all ingoing edges for all edges uv. We will say that we need to mark it. So if it is not marked yet, let's say that du equal to 1 and put it in the queue. Do I have enough space? I think yes. And if I have the winning node, again I iterate over all outgoing edges. I will decrement this counter. Let's say this out is a counter, just for simplicity. So out is the number of outgoing edges which are not marked yet. So I'll just decrement the counter. And then, if it is 0, I will put it in the queue. Sorry, cat. Oh. Perfect. Like this. Now, in the end, all the unmarked nodes are the draws. Nice. That's all. And now the time complexity of this algorithm is linear, since every time I pick some node from the queue, every node will be removed from the queue exactly once. So I do all these exactly once for each node. And here I just iterate all ingoing edges. So the total number of ingoing edges for all nodes is m. So the total time complexity will be m plus n. That's me. So we can analyze games with cycles in linear time as well. Also, we can apply both these tricks. So if you have a symmetrical game, if you have like edges of two colors and first player can only move along the red edges, second only along the blue edges, we can apply the same technique. We can double the graph and so on. And if you want to have a game when you win when you have no moves, then again you can apply the same trick we apply to the acyclic graphs. Just add one extra node, put these edges from these dead ends, and then you will apply the same algorithm and you will determine for each node if it's winning or losing. So both these tricks can be applied to graph the cycles as well. Nice. Final trick. Let's talk about grinding. We need to talk about Grandi function. Cool? Clear enough? Let's go. Let's talk about sum of games. So if you have what you may do, you may have two games and you want to calculate the sum of these games. What does it mean? Let's have two graph games. For example, let's have game A like this. Let's see, 1, 2, 3. 1, 2, and 3, and this. It's a very simple graph game. And game B, when you have only, let's say, two states, like this. Very, very simple game. So let's have two graph games. What is the sum of these games? So what is the game A plus B? Game A plus B means you have two tokens. So you have both these, you have two games. In each of the game you have a token. So you put this token here and another token here. And if it's your turn, then your move is just to move one of the tokens. Move token in one of games. Good enough. So when it's your turn, you decide in which game you need to move, and then make a move in this game. Yeah, good enough. Now, the first solution is simple. What we can do is to build another game and just encode both these states into the state of the third game. So we can take all the pairs of these states. So our current state is in this sum. So if you have the sum, your state is the pair of states. You have state in the first game and state in the second game. Let's encode all these pairs as states in our new game. So let's have a game of 6 states. So we have 6 possible states in this game, right? So let's build a graph of 6 nodes. Let's have 1, 2, 3 here, 1, 2, 3 here. So this will be the state of the first game. So state of the game A. And here you have the state of the second game. Nice. And now you just simply apply these moves to this graph. So you're standing here. You can make a move in the first game and move to the second or to the first state. So if you have state 1-1, you can move to state 2-1 or to state 3-1. Yes, you can move here or you can move here. Again, if you stand here, it means you have tokens here and here. And if you make move in the first game, you can move here or here. If you make move in the second game, you can move to this state. And so on. So if you're standing here, you can move here or here, and so on, and all other, like this. So this will be the graph, which is the sum of this graph. Yeah. Well, this is like a product of two graphs. Something like that. Now, this is a cyclic graph. So if you have two acyclic graphs, if you make product of this graph, you will have some acyclic graph. So you can analyze this graph using the same technique as before. So in this graph, you can just make a topological ordering and just go from right to left and analyze this graph as before. So this will be the losing state, this is a winning state, this is winning, this is losing. Here you can move here, so it's winning, and this will be a win. That's all. So again, so the first solution is very simple. You just encode each pair of the states as a state in a new game, and then you analyze the game as a simple graph game. Again, this is a graph game, like before. So we just can analyze it in the same way as we analyzed the games before. So the sum of two games is sum of two graph games is a graph game. So we can analyze it as before. Yeah. Good. But the size of the graph is increased. So if you let's say you have two graphs of size n, then the size of this graph will be n squared, right? And if you n squared is not don't look that big, but if you have many games, if you want, for example, calculate the sum of 3 games like this, you can calculate sum of 3 games. What is sum of 3 games? It's sum a plus b plus c. Yeah. So a plus b is a graph game, so we can make a sum of 2 games and another game. That's simply what does it mean? You can make move in C or in one of the games A or B. It means you just make a move in one of these 3 games. So it's so if you want to calculate the sum of multiple games, then this power of n will just be increasing. So the number of states here will be n cube and so on. So if you want to have sum of 5 games, you will have n power 5 and so on. So the size of this graph will increase exponentially if you increase the number of games you have. And that it's not what we want. So I want to be able to analyze a big sum of games. So I want to so basically let's have a break. So why do I want to analyze sum of games? Usually that's you want to do it in situations when you want to, let's say, you have some game and you want to determine if the game is winning or losing. So you want to just split your games into separate independent games and then calculate this game independently and then calculate the sum of these games. That's what usually going on. So usually you have some game which has too many states, so it's very hard to analyze. You want to split this game into sum of some small games, then analyze each of these small games, and then find the sum of these games. So what I want to do is to analyze these 2 games separately, and then somehow calculate the sum of 2 games. So, for example, let's say you have 2 games and you know that both these games are losing games. So you have this game A with this such and thing and this game B. And you analyze both these games independently. You don't build this graph. You just analyze this game and analyze this game, and you found out that both states are losing states. Both these games are losing games. You lose here and you lose here. What will be the sum of these two games? What do you think? So you have two losing games. So in both these games you lose. What will be the sum of these games? Will it be winning or losing game? Any guesses? Just two options. Okay, you guessed that's right. So this will be a losing game. So if you have two losing games, you will have a losing game. Let's prove it. It's actually quite easy to prove. So imagine you're the first player. So you need to make a move in one of these games. For example, you make move in game A. So in game A, you make any move. Since it was a losing state, we will make a move to some winning state. So the first player always make a move from some losing state to some winning state. Now it's the second turn. So that's the second player's turn. So what he can do is to move from this winning state to some losing state. So he will make the move in the same game, and again he will move you to state when you have two losing states. So again, first player make any move. Now second player makes the move in the same game and moving again to the losing state. So the first player always have two losing states. So at some point you will go to some final state, so you have no moves, and you will lose the game. Yeah. Okay. Case number 2. What if you have losing game and winning game? So let's say here you have losing game, here we have a winning game. What will be the sum of these games? Yes, the sum of these two games will be the winning game. So if one of the game is losing game, another game is winning game, then the sum of these two games will be winning game. Well, because in this game you can move to some losing state. And now the second player has two losing games, so he will lose, because sum of two losing games is a losing game. So sum of losing and winning games is a winning game. Okay, and finally, if you have two winning games, what will happen? Yes, if you have two winning games, the result may vary. So it depends on the game. So there are, for example, if you have two games like this, then both these games are winning games. So this is a winning game, this is a winning game. But the sum of these two games will be a losing game, because first player moves here, second player moves here, first player loses. But if you say have something like this, not like this, like this. Like we have this game. So in this case, we have two winning games, and the sum of these games is a winning game. So sometimes it's losing game, sometimes it's a winning game. So that's basically all we need to think about. So again, how to analyze the sum of two games. We analyzed each of these games independently, and in the only case when we don't know what will happen in the sum of these games is when we have two winning games. If we have two winning games, we need to find some stronger theory to analyze these games. Yeah, we'll talk about the score. Yeah, I'm just giving some intuition about its function before I will introduce the Grandi function. I want to give you some intuition because so you need to understand from what arguments this Grandi function came from. What's the Grandi function? So Grandi function works like this. So it turns out that actually the result of this sum depends on some kind of type of winning game. So if you have two games of the same type, like here, here we just have two similar games. So if you have the sum of two equal games, so if you have game A and game B, you have the same game here. Let's say A plus A. If you have two equal games, then the sum of two equal games will always be a losing game, because the second player can use the symmetrical strategy. So you make a move in one of the games, and your opponent will make the same move in another game. So sum of two equal games is always a losing game. And it turns out it depends on some kind of type of your winning game. So if you have two winning games of the same type, then the sum of these games will be a losing game. If you have two winning games of different types in some way, then you will have a winning game. So that's basically how it works. Okay, let's move to the Grandi function. The Grandi function works like this. Let's have a node B. The Grandi function, say G of V, will be a max of all Grandi function U for all edges BU. Ta-da! That's the Grandi function. Very easy. What is max? Max is the minimal non-negative integer number which is not. Max is minimal non-negative integer not in the set. Yeah, good enough. So you have all these edges. For each edge, you know the Grandi function of these nodes. Let's have you have some node. You have all these possible transitions. So for each of these nodes, you calculate the Grandi function. Since the graph is acyclic, you can calculate them from right to left. If you have cycles in the graph, it's much more complicated theory about this. Highly recommend. So if you want to know how to calculate sum of two games with cycles, nice theory. Much more complicated than this. So what's going on? So imagine for each of these nodes, you already calculate the Grandi function. Let's say Grandi function here is, let's say some 2, 0, 1, 2, and 5. So what will be the Grandi function for this node? Again, we need to find the minimal non-negative number which is not in the set. So we have 0 in the set, we have 1, we have 2 twice, but we don't have 3 in the set. So 3 is the minimal number which is not in this set. So Grandi function for this node will be 3. That's all. Now let's calculate Grandi function for this, for example. So for this graph. Let's calculate for all these graphs. Root m time? No, you can calculate function in root m of m. No, the value of Grandi function can be more than square root of m. That's true. But actually, you can calculate in linear time. How to calculate Grandi function? We can calculate Grandi function in linear time. How to do it? Let's go from right to left. Each time we take a node, take all outgoing edges. We need to find minimal number which is not in this set. What we can do? We can, here, we have 5 nodes. Yeah. So we have, here we have 5 nodes. So we know that the minimal number which is not in set will be at most 5. Because if you have integers from 0 to 5, there are 6 integers and you only have 5 nodes. So you know the value of Grandi function for this node is at most 5. Now, you can make array from 0 to 4. And just mark all the values you have in this set. Again, the size of this array should be at most 5, since you have only 5 edges. Now you simply mark all the, so you have value 2, you mark it here. You have 0, mark it here, and so on. And now in this array you find the first unmarked value. So you go from left to right and find the first value which is not marked. Again, the size of this array should be at most the number of edges you have here, because that is the maximal value you can have as a Grandi function. That's all. So you can calculate Grandi function for this for this node in linear time by number of these edges. And total number of edges is m, so the total time you need to calculate the Grandi function is actually linear. Yeah. Also, you can optimize it a little bit. Yes, the maximal value of the Grandi function will not increase the square root of m. You can prove it as an exercise. Yes, that's also true. Right. Oh, okay. I'll just put it here. So, Grandi function of y will be no more than square root of m. Oh. I'm not sure about constant factor. Let's say big O. Like this. I'm not sure about constant factor there. There must be some constant. Yeah, doesn't matter. Let's move back. So let's try to calculate Grandi function for these graphs. Let's start from these graphs. So this is a very simple graph. So this node has Grandi function equal to 0. And since you don't have any outgoing edges, the minimal number you don't have is 0. You don't have any numbers here. From here you can go to 0, so minimal number you don't get is 1. Here it is 0, again here you get 1. From this node you can move to 1 and to 0, so minimal number you don't have in this set is 2. So Grandi function for this number is, for this vertex is 2. No, I believe this is true. Oh, okay, try to think about it. Now let's move to this graph. What's happened in this graph? So here you have it. So here is 0. From here you can move there. You can move to 0. So Grandi function is 1. Here you can move to 0. So Grandi function is 1. And here you can move here and here. So you can move to 1 and to 1. So the minimal number you can go is 0. Here you can move to 1 and 0, so it's 2. And finally for this node you can move to 0, to 1 and to 2. So your minimal number you can go is 3. So Grandi function will not is 3. Nice. Now, how this Grandi function is connected to the state of your game. So we want to determine if the game is winning or losing, but now we have this Grandi function. How is Grandi function connected to the state of the game? Very simple way. The game is losing only then if and only if the Grandi function is 0. So Grandi function is 0 if and only if the V is losing state. Now let's prove this. It's actually quite easy to prove. So let's say if, well, let's do it by induction from right to left. So we just go from right to left and prove it for each node. So let's say if we have some node and the Grandi function is 0. So if Grandi function is 0, it means you don't have 0 in the set of Grandi functions for these states. So all these states are non-zeros. So all these states are non-zeros. But by induction, if the Grandi function is not 0, it means all these games are winning games. So you must have a losing game. So if Grandi function is 0, then you have a losing game. If your Grandi function is not 0, what does it mean? It means the minimal number you cannot go is not 0. It means the 0 is in the set. So if your max is not 0, it means you have 0 in this set. So there is some node with Grandi function 0. What does it mean? It means by induction, this state is losing state, so your state must be a winning state. That's all. So if Grandi function is 0, then your state is losing. If your Grandi function is not 0, then your state is winning state. That's all. So basically, Grandi function is like, how it's called? It's like more interesting version of this previous solution when we decided. So we just replaced these ones with some integer numbers. So zeros, again, are the losing states, and all positive numbers are some different types of winning states. So Grandi functions simply want to just split all the winning states into some classes, like before. Do we have time for this? No, we don't have time for this. Nice. That's all. And now the final thing. What I want to do is to calculate Grandi function of some of the games based on Grandi function of two separate games. Again, what I want to do, I want to analyze games A and B separately, and then analyze the sum of two games without building this big graph. And it turns out it's very simple. It turns out that the Grandi sum, or Grandi of sum of two games, is just basically the bit XOR of these two. So we just take these two numbers and make a bitwise XOR of these two numbers. And it will be the Grandi function of this sum. That's the magic. That's just the magic. So if you look here, what's going on? So here, for states of the first game, we have Grandi function 2, 1, and 0. And here we have 1 and 0. Yeah. I have 1 and 1. So now this 0 is just a sum of this 1 and 1. And this 1 is just sum of this 1 and 0. And this 3 is just XOR of this 1 and 2. So 1 XOR 2 is 3. So that's why we have value 3 here, and so on. This 2 is 0 XOR 2. This 1 is 0 XOR 1, and so on. Because that's a nice thing to say everything is clear at least every minute. So I know that you understand what's going on. Yeah, that's the rules of these streams. That's all. Now we just need to prove this, and that's all. So again, if we prove this, and I will prove it in just a second, then how to analyze the sum of two games? Again, you have two separate games, and you analyze this sum of two games. So what you do, you analyze the first game, find this Grandi function. Analyze the second game, find the Grandi function. And then you just calculate the Grandi function of this sum as bitwise XOR of these two numbers. And you don't need to build this graph. Yes? You just build these values, and now you know all these values as well, as XOR of these two numbers. That's all. let's prove this. Sorry, okay. Nice. Well, let's go. So let's look at sum of two games. So we have this sum of two games. So we have game A. We are starting in state A, and we have this game B, and we are now starting in state B. So what moves can we make? So the current state is AB. What moves can we make in this game? We can make one of the moves in the first game, yeah, or one of the moves in the second game. So if we make move in the first game, we will move to some state A prime B. So if we make the move in the first game, or we can make move in the second game, then we'll move to state A B prime. Now we just prove it by induction. We go from right to left. For these two games, not two games, so we have some of the games like this. For all these games, we already know that this formula is correct. So we know that the Grandi function for this state is actually GA prime XOR GB. And we know that the Grandi function for this state is GA XOR GB prime. So again, this is our current state. From this state, we can move to one of these states. For these states, we already proved that the Grandi function for these states looks like this, just by induction. And now we just need to find the minimal number which is not in this set. And we just need to prove that this minimal number is actually G of A XOR G of B. So we need to prove that GA XOR GB not in set, not and all numbers less than this number GB are in set. So we consider the set of all possible moves, and we need to prove that this number is not in this set and all smaller numbers are in this set. Then it will prove that the Grandi function for this state is actually this number. That's what we need to prove. Well, let's prove this. Let's prove the first thing first. I claim that if we consider all the numbers like this, there may be not a number like this in this set. Why it is true? Well, let's say, if we have a situation like this. So let's prove the first thing. If we have a situation like this, so we have some move which have the Grandi function like this. So for example, move of this. And so if we have this XOR equal to our XOR. I claim it is impossible, because if you have this XOR equal to this XOR, you can XOR both sides by the value G of B, so you can just eliminate these two, and now you have just Grandi function of A prime equal to Grandi function of A. It means that in game A you have a move from A to the state with the same Grandi function. You can make move to this to the state with the same Grandi function. So G of A prime shouldn't be equal to GA. Now if you calculate Grandi function right? So G of A shouldn't be equal to G of A prime shouldn't be equal to G of A. It means it is impossible. Yeah? Impossible. So this XOR is definitely not in this set. Clear enough? That's an easy part actually. Again, if you consider the set of all possible sums like this, in this set, there never will be this sum. Because if this sum is in this set, it means that either one of two things happen. You may have this g of a prime equal to g of a. You can't have this because you never move to the state with the same Grandi function. Or you can have g of b prime equal to g of b. That's also impossible. Yeah. Okay, that's the first one. Second is a little bit more complicated. Oh, let's go. So one of these is proof. I can do it like this. So let's do it like this. Let's look at these numbers as bit numbers. So we have g of a, g of b, and their XOR, and some number which is less than this XOR. So let's look at the bitwise representation of these numbers. Now let's see. So again, we took these Grandi functions of a and b, calculated the XOR of these two numbers, and then take any number which is less than this XOR. Let's find that. So one number is less than a number. How does it look when you look at the bitwise representation of this number? So if one number is less than a number, then if you look at the bitwise representation, they have the same prefix. And then you have 0 here and 1 here. Yeah. So if you look at any two numbers, such that one number is less than a number, then you have the same prefix, then you have 1 here and 0 here. That's how you compare the numbers in binary, right? Now, let's see how these two numbers look. So this one is XOR of two bits from A and B. So one of these bits should be 1 and another should be 0. Let's say, for example, this is 0, this is 1. And here you have some prefixes. So we have, well, let's say, I'll use different hatchings for different numbers in case the colors are not perfect. And something like this. Let's like this. So these numbers g of a and g of b contain some prefix, and then here one of them contained 0 and one of them contained 1. So the XOR of these numbers is the XOR of these two prefixes plus the XOR of these two bits. And now what we will do, we will take the number which contains 0, this b, and XOR this x with this element. So we will calculate XOR of x and g of b. So what will happen if we XOR these two lines? So we XOR this line and this line. No, for example, this bit will be 0, obviously. Yeah. What will happen in this prefix? This prefix will be XOR of this blue prefix, yes, and this green prefix. So if you XOR this blue prefix and this green prefix, you will get this red prefix. So the prefix of this XOR will be the same as in GA. So here you have this green prefix. So this prefix will be the same as in number GA, right? So since this blue prefix is XOR of these two prefixes, so this blue is XOR of red and green. So if you make XOR of blue and green, you will get red. Because XOR eliminates itself. If you apply XOR twice, you will have the same. That's all. That's all. And now just look at this number. I claim this number is less than GA. So we just proved that if we take XOR of these two numbers, it will be less than G8. What does it mean? It means that from the state A, we can move to some state which have this Grandi function. So we have, so in game A, we can move to some another state such that Grandi function of A prime will be equal to this XOR. And it just means that if we move to this state, then G of A prime XOR G of B will be equal to X. That's all. So we just proved that for any number less than this XOR, we can make some move which give you the position with Grandi function equal to X. So we can move to any position with all Grandi function less than this number, and we cannot move to position with Grandi function equal to this number. It means this number is the smallest number which is not in this set. So it is the Grandi function of this sum. That's all. Clear enough? Okay, hope it's clear enough. Thank you for joining me today.